Hey students, are you wrestling with complex numbers? This video is your complete, step-by-step guide to solving exercise 1.2 problems from your Class 11 textbook. Start with z. We start by defining our complex number. Z equals x plus iy. Calculate iz. Multiplying by I gives us iz equals minus y plus ix. Identify parts. The RE of iz, real part of iz, is minus y. The IM of z, imaginary part of z, is y. Conclusion. Since minus y is the negative of y, we've shown the identity. RE of iz equals minus IM of z. IM of iz equals RE of z. Use iz. Using our previous result, iz equals minus y plus ix. Identify parts. The IM of iz, imaginary part of iz, is x. The RE of z, real part of z, is also x. Conclusion. Since both sides equal x, the identity is proven. Goal. We need to prove that open parenthesis z1z to close parenthesis z3 equals z1 open parenthesis z to z3 close parenthesis. Apply laws. This proof relies entirely on the multiplicative, commutative, and associative laws of complex numbers. The process. We strategically change the grouping and order of the three complex numbers until the expression on the left is transformed into the expression on the right. Conclusion. The algebraic properties confirm that the grouping does not change the final product. Part 1z real implies z equals z bar. If z equals a, its conjugate, z bar, is also a, so z equals z bar. Part to z equals z bar implies z real. Let z equals a plus ib. The condition z equals z bar becomes a plus ib equals a minus ib. Solve. This simplifies to 2ib equals 0, meaning b must be 0. Conclusion. Since b, the imaginary part, is 0, the number z must be real. Substitute components. We substitute z equals x plus iy and z bar equals x minus iy into the left side. Numerator. Z minus z bar simplifies to 2iy. Denominator. Z plus z bar simplifies to 2x. Simplify left side. The fraction becomes 2iy over 2x, which reduces to I times y over x. Simplify right side. The right side is I times the ratio of the IM of zy to the RE of zx. Conclusion. Since both sides equal iy over x, the identity is proven. Rearrange. We start with z squared equals z bar squared and factor it as a difference of squares. Open parenthesis z minus z bar close parenthesis open parenthesis z plus z bar close parenthesis equals 0. Substitute components. We use the results from the previous question. Z minus z bar is 2iy, and z plus z bar is 2x. The new equation. Substituting these yields open parenthesis to iy close parenthesis open parenthesis to x close parenthesis equals 0, which simplifies to for xy I equals 0. Analyze. Since for I is not 0, the product xy must be 0. Conclusion. This requires either x equals 0 z is pure imaginary or y equals 0 z is real. Property. We use the rule that modulus of z1 z2 equals modulus of z1 times modulus of z2. Calculate modulus of z1. For z1 equals to minus 3i, modulus of z1 equals the square root of 2 squared plus minus 3 squared, which is square root of 13. Substitute. We substitute this into the given equation. Square root of 13 times modulus of z2 equals 16. Final answer. Dividing by square root of 13 gives the final result. Modulus of z2 equals 16 over square root of 13. Goal. We prove modulus of z1 plus z to squared minus modulus of z1 minus z to squared equals for RE of z1 z to bar. Expansion. We expand the left side using the definition modulus of w squared equals w times w bar. LHS simplifies. The expanded left side simplifies to 2 times open parenthesis z1 z to bar plus z1 bar z to close parenthesis. Identity. We use the complex number property that w plus w bar equals to RE of w. Connect. Letting w equal z1 z to bar. the left side becomes 2 times to re of z1z to bar, which is exactly for re of z1z to bar. Starting point. We begin with the true statement that open parenthesis modulus of re of z minus modulus of im of z close parenthesis squared is greater than or equal to 0. Expand and rearrange. Expanding and rearranging the terms allows us to show that to modulus of z squared is greater than or equal to open parenthesis modulus of re of z plus modulus of im of z close parenthesis squared. Final step. Taking the positive square root of both sides leads directly to the required inequality. Square root of 2 times modulus of z is greater than or equal to modulus of re of z plus modulus of im of z. Substitute. Modulus of 2x plus I times open parenthesis to y minus 1 close parenthesis equals 4. Square. Squaring both sides and simplifying the modulus gives the equation for a circle. For x squared plus for y squared minus for y minus 15 equals 0. Substitute. Modulus of x plus I times open parenthesis y minus 1 close parenthesis equals modulus of x plus I times open parenthesis y plus 1 close parenthesis. Simplify. Squaring and simplifying the modulus on both sides cancels out all x and y squared terms, leaving for y equals 0. Locus. The equation is y equals 0, the real axis. Substitute. This is the sum of two distances equaling a constant, which is the definition of an ellipse. Process. Substituting z, applying the modulus, and squaring to eliminate the radicals is a lengthy process. Locus. The final equation is the ellipse. 25x squared plus 9y squared equals 225. Calculate iz bar. Z bar is x minus iy, so iz bar equals y plus ix. Real part, the re of iz bar is y. Solve. Substituting this, 1/2 y equals 4. Locus. The equation is y equals 8, a horizontal line. Rationalize. We multiply the fraction by minus I over minus I to simplify the denominator. Imaginary part. The imaginary part of the simplified fraction is minus x over 2. Solve. Setting this equal to minus 5. Minus x over 2 equals minus 5. Locus. The equation is x equals 10, a vertical line. Minus 2 is less than or equal to im of z plus I is less than or equal to 3. Imaginary part. The im of z plus I is y plus 1. Inequality. The inequality becomes minus 2 is less than or equal to y plus 1 is less than or equal to 3. Isolate y. Subtracting 1 from all parts gives the final answer. Locus. The result is the horizontal strip. Minus 3 is less than or equal to y is less than or equal to 2.